Good morning, Your Highness, Your Excellencies, ladies and gentlemen. That background photograph you see before you was taken by Brian Biddy over a decade ago on the final flight of Spaceship One. And as spectacular as that photograph is, Brian says the camera cannot capture the stunningly beautiful colors discerned by the human eye. The neon blue band of atmosphere beneath you in stark contrast to the blackness of outer space. We at Virgin Galactic believe this is the view that all suborbital spaceflight astronauts long to see. But successfully getting there requires more than just a spaceship with a suitable rocket motor. For any credible and ethical company, requires suitable test data to support their precept that they have a safe system that is ready for commercial operations. After all, without safety, there will never be commercial viability. As our test program regains momentum, I would like to share my thoughts with you regarding the flight test challenges facing the commercial suborbital spaceflight industry as a whole. We demonstrate our safety through the proper mix of analyses, simulation, ground test, and flight test. Finite element analyses helps us design to the proper strength, while computational fluid dynamics helps us tweak the conceptual design into one that actually flies. Wind tunnel results can be used to spot check the CFD, but wind tunnel testing is expensive, and it is difficult to find a wind tunnel that can handle a full-size spacecraft, and impossible to find one that can handle a full-size spacecraft at high supersonic speeds. Some companies have found inexpensive solutions to low-speed wind tunnels. Skilled Composites successfully used this mobile test fixture to refine improvements to the Spaceship Two horizontal stabilizer. Most companies use CFD for the lion's share of their analyses. CFD, however, is not a panacea, and individual test case runs can take days of computer time, and small companies cannot bring to bear that level of manpower and computer power that could be levied on government-sponsored space programs. And you can have the greatest minds, computers, and wind tunnels at your disposal, but ultimately your vehicle's air and space worthiness are proven through flight test. History is rich in examples of programs where flight test did not match predictions. It is especially critical during that initial first flight takeoff where you are at the lower left-hand corner of the flight envelope, slow and close to the ground. The first flight of the F-16 was, in fact, only planned to be a taxi test, but occurred because of the large disparity between the handling qualities in the simulator and the handling qualities of the actual prototype aircraft. Most of the ground testing should be accomplished prior to flight test, although there may be some tests that can be safely delayed until later in the flight test program. Virgin Galactic intends to be in the business for the long haul, so we have invested heavily into ground testing resources.
For us, it all started years ago testing in the materials lab. We test coupons that go all the way down to a ½ inch or smaller. We have some analytical chemistry devices that are down at the 1/10 of an inch scale, where we really understand the chemistry and the fabric that we use to build our spaceships. From there, we build again to the very small coupons, joints that represent joints in the vehicle, but they're only an inch big. And we'll make hundreds and sometimes thousands of those to build up statistical understanding how those materials behave. We'll feed the information back to our designers and our analysts so that they can use it to design the large structures, and then we'll build prototypes and facsimiles of large components, and we'll test them again and make sure that they're behaving the way we think they do, that those material properties have given our analysts and our designers the right information to build the vehicle the right way. And we progressively move finally to the large assemblies that we test here in the large-scale test lab.
So this is the safety brief for the cabin ultimate pressure test. This test can apply loads to a large composite structure.
Our goal is to test to cover the entire life of the vehicle, which is literally thousands of flights. We take a statistical approach. For every flight that we anticipate in the lifetime of one of the vehicles, we'll test 4 times that on a large-scale level, and as many as 1,000 times that on a material level.
The The aerospace industry has over a century of airplane flight test experience, but there is essentially an industry standard recipe for conducting it. Things are different, however, in the world of suborbital spacecraft flight testing. For one thing, although the human race has been sending up spacecraft for decades, there have only been a few crewed suborbital space flights. If you look at the current fledgling industry, you will see that the different companies offer some dramatically different methods for getting to suborbital space. And the current frontrunners appear to be horizontal takeoff with horizontal landing and vertical takeoff with vertical landing. And while there are certainly other possibilities, I do not know of any that are beyond the conceptual design phase and therefore will not address them here. Looking at the first case, we can break HTHL down into one or two stage systems. The public typically envisions a one-stage HTHL spacecraft to be a rocket plane, but there have been proponents of using conventional air-breathing engines for that initial portion of the flight. One perceived benefit of having a jet capability is that you can power them up again for a conventional landing. But that capability comes with a large weight impact and added system complexity. There was a reason the U.S. Space Shuttle landed as a glider. It was the cost-effective solution, and safe, cost-effective solutions are paramount for commercial efforts. I can, however, see a benefit in modifying some prototype single-stage spacecraft with jet engines to facilitate early atmospheric flight testing, similar to what the Soviets did with their Buran space shuttle development program. A typical two-stage HTHL spacecraft uses the mothership as the first stage. In the lower atmosphere, the mothership's subsonic wing and jet engines are an efficient and cost-effective way to carry the load to the stratosphere. Whether the spaceship is mounted beneath or above the mothership is usually driven by sizing constraints. And there are pros and cons for each method, and both require analysis and testing to ensure a clean and safe separation and an efficient transition to rocket-powered flight. Perhaps some of the appeal for an HTHL spacecraft is that at first glance, their takeoff and landing profiles seem familiar to us, but horizontal takeoff rocket planes pose some unique challenges in flight test. How do you do that first flight, an envelope expansion? As an example, whether it's a single-engine general aviation aircraft or the Boeing 787 you see there, the typical first flight is a moderate power climb into the heart of the envelope of speed and altitude. The goal of that first flight is usually simply to land safely and verify that the aerodynamic reality is a sufficiently close match to the pre-flight predictions. On first flight, configuration changes are minimized. The landing gear is normally left down, and the aircraft is flown conservatively with smooth inputs and gentle pitch and roll attitudes. But a rocket plane capable of space flight requires a high acceleration, and thus you need to quickly point the nose towards the vertical and raise the landing gear to keep from exceeding limits. The only way to avoid such aggressive maneuvering is to have the capability to burn at a minor fraction of that total thrust capability. And in any event, the flying qualities challenges must be met while in that higher risk region close to the ground. And any shutdown of the rocket motor should be done with sufficient time to perform all the required cleanup items, such as dumping unused propellants prior to the high workload landing phase. There is no simple solution. Perhaps a good compromise would be a reduced thrust climb at a constant airspeed to sufficient altitude whereby the engine would be shut down and the glide profile began. And then on subsequent flights, you could use a similar climb profile to higher altitudes and higher glide speeds to expand that flight envelope. If the engine is easily restartable, then you may be able to accomplish more test points on a given mission because you have the luxury of doing multiple climbs and glides in a single flight. It is always prudent to do taxi tests prior to your first flight. In an airplane, you typically verify the ground handling and your brake performance at a very slow speed, and then you speed up and repeat in, say, 20-knot increments towards takeoff speed. Stabilizing at such speeds would be impossible in a rocket plane. We believe that the two-stage mothership concept serves as risk mitigation for that first flight. The spaceship is released from high altitude at a conservative speed and the pilots fly a conservative profile with plenty of time to verify that the performance and stability and control match predictions prior to committing to the approach and landing. We also believe that the flight is safer without the added complications of a running rocket motor. Prior to Spaceship Two's first flight, we did a series of tow taxi tests behind a large truck to verify the low and medium speed ground handling qualities and the performance of the steering and braking systems. Another benefit of the two-stage concept is you can use the captive carriage capability as a way to get a lot of flight time on the vehicle in an operational environment. You can fly for hours, and we have, at high altitude to cold soak components and verify the nominal and backup systems perform at the extreme environmental conditions. Examples of representative captive carriage flight tests would be electrical system capability, the capability of the environmental control system to control temperature, humidity, and carbon dioxide, the performance of anti-ice or anti-fogging systems, avionics, navigation and display modes, reaction control system performance, and rocket motor system management. You can also move the flight controls under aerodynamic flight loads and get hinge moment and stability and control data. Initial releases should be conservative and use a trim and control positions and airspeeds that maximize the chances of a clean separation. If the reality matches the predictions, then you can slowly build up to release conditions that are the optimum compromise between operational mission goals, such as maximum apogee, while maintaining suitable safety margins. It was a good day. With the mothership air launch configuration, you need to properly design for, analyze, and test as appropriate for abort capability on the runway, as well as ensure you have proper stability and control and climb performance in the event of an engine failure on takeoff on the mothership. You also need to define other what-if situations to include an inadvertent release, the minimum safe release altitude, and mated landings. There was another concept for a multiple stage horizontal takeoff and horizontal landing idea proposed in the 1990s that used an aerotow to altitude as the first stage of an orbital space plane. I was the project pilot for the concept demonstrator seen here on the right. This aerotow concept can also have an application as a cost-effective means for risk reduction flight test of a prototype single-stage HTHL. Of course, this concept has a unique blend of risks versus rewards. Like the first flight of a typical powered airplane, you're initially demonstrating the spacecraft is flyable while in that low-altitude, high-risk regime. The pilot is also flying the higher gain task of maintaining the tightly constrained tow position. And like conventional sailplanes, you must always be prepared for the tow plane to have engine troubles and always be ready for an early release from tow. Lastly, some prototypes have been dropped from a helicopter for their first flights. Perhaps a good solution would be to do a couple of helicopter drops to verify the approach and landing capabilities, and then use a more conventional aerotow to clear the much larger envelope for the gliding flight portion. Independent of the number of stages, careful consideration has to be given to the abort modes, as well as any regions in the flight envelope that might be impudent to dwell within. What are your takeoff abort limits? Can you shut down the rocket motor at takeoff speed and then stop within the remaining available runway? What is the minimum altitude or energy state where you can handle a motor failure and recover to a gliding approach for an unpowered approach and landing? How many of these cases do you test for, and which cases do you decide that it's better not to test and instead clear it through analysis and then document it as an acceptable risk? As an example seen here, the Space Shuttle astronauts did extensive training in the simulator for the return to launch site abort mode, a maneuver that was deemed too risky to ever flight test. Next, let's discuss VTVL, vertical takeoff, vertical landing. I'll break these down into two categories: single stage takeoff and land, and single stage takeoff with a separate stage landing. An example of the former was a proposed DCX that did some low altitude flights in the 1990s. An example of the latter is Blue Origin's New Shepard. I think VTVL appeals to some of us because it was envisioned by the early science fiction writers. And you can debate whether it is the best choice for a reusable suborbital spacecraft, but it's hard to dispute that we ultimately need that to develop this kind of capability for extraterrestrial missions. In the case of vertical takeoffs, you do not need to worry about any build-up taxi tests or high-speed runway aborts. You do, however, need to worry about low-altitude escape capability, and that is usually handled by some kind of launch escape system. The Mercury capsule on the lower left used a powered tractor system, but modern designs use integral pusher rockets. And in all cases, it is an extremely dynamic ride that, although life-saving, will likely be a rather traumatic customer experience. In the case where a capsule separates for a parachute recovery, then you need to define the requirements and whether it will touch down on land, water, or both, and the allowable wind constraints and allowable dispersions. And ground testing can be very involved and require expensive infrastructure. Let's look at some of the flight test challenges of powered landings. For one, the spacecraft requires a large amount of energy, and the current technology, that means thousands of pounds of fuel. And like its single-stage horizontal takeoff brethren, a single-stage vertical lander takes off with a high fuel mass fraction and must land with a low one. Landing at such a light weight requires either a highly throttleable rocket motor or using a reduced number of thrust chambers. NASA astronauts like Dr. Aldrin had a lot to deal with when they landed on the moon, but thankfully they did not have to deal with aerodynamic instabilities, transonic effects, or crosswinds. The relatively low lunar gravity also enabled them to perform a controlled, manually piloted descent. In the case of suborbital space tourism, you have the additional constraints of aerodynamics and winds. And in Earth gravity, you likely will not have the luxury to carry enough fuel reserves to handle a slow and controlled descent. So we are forced to use a mix of drag devices, thrust vectoring, and sophisticated automation to retain stability during the rapid backwards descent. Vertical landings are full of drama and suspense, with an extremely precise last-second burn to arrest a meteoric rate of descent and softly land on the spot with little reserve fuel. And to complicate this already incredible process, in those last few moments, the landing gear are deployed with minimal time to deal with any malfunctions. All spaceflight contests must put proper thought into identifying all of the potential hazards and the ways to mitigate them to acceptable risks. Flutter is typically a concern for high-speed aircraft, and any predicted flutter regions within the normal flight envelope must be thoroughly tested for. How big of a chunk of the flight envelope can you clear per flight? Flutter, Mach effects on stability and control, aerodynamic heating, and structural loads are just some of the elements that feed into that decision. One rule of thumb that NASA used as they approached the design speed of the X-15 suborbital rocket plane was to limit their speed expansion between flights to 1/2 of a Mach number. They elected to waive that requirement on the flight where they set the maximum speed record of Mach 6.7, and they nearly lost the vehicle because of that, due to heat damage. You should not declare your spacecraft ready for commercial service just because you have demonstrated a couple of successful space flights. You need to demonstrate operational missions with repeatability and pre-planned variances that encompass the natural variability between pilots, the spacecraft, and the environment. A fully staffed control room is expensive and labor-intensive. If the operational mission can be done with reduced monitoring, then the sophisticated automated caution, warning, and advisory system should be implemented to alert the pilots to off-nominal systems or performance and reduce their monitoring workload. And even after declaring operational status, there will likely be follow-on testing required as the system continues to mature and changes are made to subsequent models of the aircraft. And with that, I thank you for your attention and open it up to any questions or comments.